Good morning. Today, I, Ruben Leoncio, and my colleague Aiden Garcia will be presenting the topic Distribution Automation as part of the Transmission and Distribution course taught by Professor José Cedeño in the University of Puerto Rico at Mayagüez. To start, let's delve into the intricacies of distribution automation. Distribution automation refers to the systematic implementation of automatic processes within the electrical grid to minimize human involvement. These automation strategies are not only localized that are typically applied to radio systems, but also extended to grid-wide application, particularly in prevalent inlet systems. To go deeper into the intricacies of distribution automation, it's imperative to conceptualize it within the framework of electrical grid from an automation perspective. The electric grid, perceived from that standpoint, encompasses power generation, transmission, and distribution. This elaborate network shoulders the crucial responsibility of delivering electricity to residences, commercial establishments, and industrial sectors. Viewed through the lens of distribution automation, it is better to characterize the electric grid as an electrical network. This nomenclature reflects the dynamic and interconnected nature of the system, underscoring the role of distribution automation in optimizing its functionality and efficiency. It can be separated in three main points. First, the grid infrastructure, the second, the electrical components, and the third, the control centers. To go deeper in these topics, I will leave you with Aiden.
Now, let's delve into the grid infrastructure, particularly the critical role played by the transmission infrastructure in electric utilities. This infrastructure serves as a linchpin for delivering voltage effectively. Its purpose is to transport voltage from a high level strategically, minimizing energy losses during transmission. This journey concludes at the primary side of the distribution transformer, a pivotal point in electric distribution process. The backbone of any efficient electrical system heavily relies on the robustness of the transmission grid. To illustrate, let's consider Puerto Rico's unique setup. The system is thoughtfully divided into various voltage classes spanning from 230 kV to 38 kV volts line to line. Notably, the majority of the transmission lines in our network are designed to be overhead, showcasing a careful balance between efficiency and functionality in our grid infrastructure for electric utility. As we continue on the grid infrastructure, our focus now shifts to the crucial distribution aspect. Starting from the transmission line, we undergo a transformation of voltage to a level more suitable for efficient energy distribution. This phase involves the distribution of energy to end users through the use of distribution transformers. However, it's important to note that this segment of the system is inherently susceptible to failures. The vulnerabilities arise from the intricate topography and complexity of the distribution lines, posing a distinctive challenge for the overall system to navigate and overcome. This challenge emphasizes the need for robust planning and maintenance strategies. Taking a closer look to at Earth scenario in Puerto Rico, the distribution system closely mirrors the transmission system, predominantly featuring overhead configurations. The system is entirely divided into different voltage classes, spanning from 13 kV to 4.16 kV volts. Moreover, to ensure energy delivery is organized in various phases. This can range from one phase to three phases. This intricate arrangement showcases the careful consideration and engineering involvement in delivering reliable energy to customers. Shifting our focus to the sources of energy that drive the generation of electricity within electric utility landscape. The energy we employ for this purpose can be categorized as either renewable or non-renewable. This diverse range of sources is strategically harnessed to produce electricity, and a noteworthy technique employed by the majority of generators involves the use of AC synchronous generators. Examining the energy landscape in Puerto Rico, a substantial portion of our energy is derived from these sophisticated generation methods. In fact, it is so significant that we depend fully on seven key energy centers. However, the commitment to sustainable and resilient energy future do not stop there. The remainder of our energy needs is fulfilled by tapping into various sources. These include harnessing the power of solar energy through dedicated solar farms, leveraging conventional hydroelectric methods, and exploring other renewable sources. The result is a carefully crafted and diverse mix of energy resources that collectively power our grid, ensuring a reliability and sustainability for the residents of Puerto Rico. Now, let's delve into the critical aspect of transforming voltage to sustainable level within an electric utility framework. Achieving this transformation necessitates a facilities equipped for such tasks. And as discussed in previous slides, substation playing a pivotal role in this process for both transmission and distribution of energy. Within a substation, a myriad of devices is deployed to effectively execute the voltage transformation. This equipment encompasses transformers, relays, potential transformers, current transformers, and more. Each play a distinctive role ensuring the smooth and efficient operation of the utility system. To put this in perspective, consider Puerto Rico, where we boast over 280 substations. These facilities are not merely structured but essentially components for the transformation and operation of our utility network. This presence signifies the integrated and well thought out infrastructure required to maintain the integrity and reliability of the electric system, ensuring that voltage is not only transformed but also effectively managed. Effectively managing the various challenges inherent in a distribution system requires a strategic deployment of diverse components. To monitor and regulate the energy consumption of customers, we employ meters. However, for more complex issues preventable in distribution system, we integrate specialist components to expedite repair time and minimize outage. One such component is the fault curve indicator, a technology designed to swiftly locate faults, reducing the time needed for repairs to further mitigate the impact of customers during fault. We incorporate fuses, breakers, and relays into our distribution systems. These components work together to limit the number of customers affected by a fault. In the continuous effort to enhance the resilience of distribution grid and reduce outage duration, we implementing robust components such as the intelligent reclosers. This advanced technology, available in both three-phase and single-phase configurations, play a key role in resolving challenges within the distribution grid. By intelligently managing fault, and the intelligent recloser act as a fuel-saving mechanism, contributing significantly to minimizing distribution and expediting the restoration process. It is a testament to the commitment to implementing innovative solutions that enhance the reliability and efficiency of our distribution systems. In the realm of energy transportation within electric utility system, a crucial and indispensable component is the cable used for the transmission of energy. Electric systems deploy various types of conductors, carefully chosen based on the anticipated load and particular circuit, whether it be for transmission or distribution. Zooming in the use of conductor in distribution system, the size and length of a conductor become a paramount factors. These aspects hinge on the topography of the land where the feeder will be situated and the magnitude of the load that the conductor is expected to handle. Effectively planning in the distribution circuit entails considering load shifting between feeders. This is especially vital for ensuring the protection and coordination of feeders. Achieving good coordination is necessary and understanding of various configurations of a feeder can adopt based on a load shifting. This consideration is crucial not only for planning the placement of fuses and the intelligent interrupters, but also for safeguarding against potential issues related to the feeder capacity to handle the design voltage rating for the conductors. This comprehensive approach ensures the reliability and efficiency of the distribution system, aligning with our commitment to delivering a robust and resilient electric utility system. A functioning electric utility system is not self-contained. It requires the oversight and management of sophisticated control centers. These centralized hubs play a critical role in monitoring and orchestrating the various elements of the system, ensuring a seamless operation from energy generation to distribution. In the realm of primary control, the focus lies on real-time monitoring and efficient management of energy demand and generation. This entails constantly adjusting and adapting to the dynamic needs of the grid. As demand fluctuates, the primary control ensures that the energy supply remains in harmony with consumption, optimizing the overall performance of the system. The secondary control aspect on the responsibility of balancing an active and reactive power. By optimizing power factor, it enhances the efficiency of energy consumption. Additionally, it integrates distributed energy resources technology. These technologies are essential for decentralized energy production, incorporating renewable sources and minimizing stress on traditional generation sources. Furthermore, the control center tertiary control function is dedicated to the long-term optimization of the electric grid. This involves strategically planning for the generation of operation and load management, anticipating future demands and ensuring the grid adaptability to evolving energy needs. Collectively, these control mechanisms operate synergistically within the control center, facilitating not only the effective flow and consumption of energy, but also promoting resilience, sustainability, and responsiveness within the electric utility system. It underscores our commitment to deliver a comprehensive and forward-looking energy infrastructure that meets the needs for today and anticipates the challenge of tomorrow.
To truly implement distribution automation, we need to take into consideration the grid infrastructure, the electrical components, and the control centers. Since when is distribution automation a thing? It began in the early 20th century with the introduction of automatic switches and relays. In the 60s, we saw the emergence of remote control and monitoring systems. In the 21st century, smart grid technologies and a communication system revolutionized the field, allowing the more efficient and reliable power distribution. Some milestones include the development of SCADA, also known as the Supervisory Control and Data Acquisition System, in the 70s, the integration of technology in the 90s, and the widespread adoption of smart meters in the 2000s. Nowadays, electrical distribution automation is the forefront of technological innovation. Smart grids, advanced sensors, and real-time analytics enabling precise monitoring, grid fault detection, and automated responses. Recent breakthroughs include the artificial intelligence for predictive maintenance, advanced grid-edge technology, over decentralized control, and integration of electrical vehicles into smart grids. These developments are driving the evolution of electrical distribution automation toward a more intelligent and adaptive system.
In delving deeper into the intricacies of electric utility system, it's crucial to examine the dynamics between manual distribution systems and their automated counterparts. Modern distribution systems, while functional, often demand more time and effort to execute various procedures necessary for the efficient management of the electric grid. The manual nature of this system can lead to delays and challenges in adaptability to dynamic situations that may arise within the distribution system. On the other hand, the evolution toward more effective and efficient grid management involves the integration of components within adaptive capabilities. Automated systems play a pivotal role in enhancing the electric grid responsiveness. This system can swiftly and intelligently adapt to different situations, optimizing grid performance. The shift toward automation introduces features like real-time monitoring, rapid fault detection, and seamless coordination between various components. This not only reduces the response time to issues but also enhances the overall reliability and resilience of the grid. As we explore further, we'll delve into the specific advantages, challenges, and considerations associated with automated distribution systems. Understanding these nouns is critical for comprehending the intrinsics of modern electric utility systems in their evolution toward more adaptive and responsive grid management. Now, let's explore the essential difference between traditional automation systems in responding to grid issues within electric utility systems. In a traditional system, the response time to the grid issue or outage typically hinge on manual detection and a human intervention. This process can be inherently time-consuming as it involves identifying the problem, dispatching personnel, and implementing manual fixes. That resilience on human intervention introduces a potential delay in addressing grid disturbances which may impact the overall efficiency and reliability of a system. In contrast, automation systems represent a transformative approach. These systems are designed to continuously monitor the grid using advanced sensor and technologies that they can shift and automatically detect deviation or fault in real time, enabling a much faster response to grid issues. The immediate detection and capability of automation systems significantly reduces the time it takes to pinpoint and address problems, leading to enhanced grid resilience and minimized downtime. As we move forward, we will delve deeper into the specific benefits and implications associated with the adopting automations in electric grid system. Understanding the advantages of automation is crucial for grasping how this system contributes to a more responsive and reliable and efficient grid management. Let's further dissect the comparison between manual process and automation technology with the context of electric utility systems. Manual processes being reliant on human intervention inherently carry a higher risk of errors. The accuracy and consistency of responses are subject to the limitation of human judgment and the potential for oversight. In a scenario where quick and precise action are required, manual process may fall short due to the inherent variability in human performance. On the other hand, automation technology brings a paradigm shift to precision and consistency. These technologies are designed to operate with a high level of accuracy, providing consistent measurements and responses. Automation systems rely on predefined algorithms and parameters, ensuring a uniform and reliable approach to monitoring, detecting, and addressing issues with the electric grid. The reliability of automation technology becomes especially crucial in situations where immediate and precise actions are essential to maintain the sustainability of the electric utility system. As we delve deeper, we will explore how these characteristics impact the overall effectiveness, efficiency, and resilience of the grid, shedding light on the transformative potential of the automation in modern electric utility system. Now, now, let's consider the critical aspect of response time in the context of human intervention and automation systems with electric utility systems. Human response time can be subject to variability influenced by factors such as ability of personnel and the need to travel to the site of the issue. In situations where is of the essence, this variability can lead to delays and addressing grid disturbances. The necessity of physical presence at the location introduces an inherent limitation in terms of speed and immediacy. Constrainingly automated systems redefine the landscape for response time. These technologies are capable of instant response and they operate in real time and can detect, analyze, and respond to grid issues without the need of human intervention on site. The aspect of which automation systems can identify and act upon deviation or fault contributes significantly to the overall resilience and reliability of electric utility systems.
Building upon our exploration of key themes such as moderation and technology in the realm of electric utility system, let's delve into the transformative impact of a specific technology on the grid operations. The integration of smart grid technology is at the forefront of enhancing efficiency and reliability. By incorporating digital communication, advanced sensor and control technologies, a smart grid facilitates real-time monitoring and dynamic management of electricity distribution. These not only moderate energy uses but also optimize the load distribution, reducing wastage and enhancing overall grid reliability. Interconnection, another crucial phase, involves linking different parts of the grid to bolster reliability and resilience. This strategy creates redundancy and alternative pathways for electricity flow. In the face of these disruptions, interconnection enables a seamless transfer of power between connected regions, minimizing downtime and fortifying the reliability of the grid. The inclusion of renewable energy sources such as solar and wind, along with energy storage solutions, play a pivotal role in furthering sustainability. Renewable contribute to a cleaner energy landscape while energy storage, like battery, helps moderate the intermittency associated with these sources, ensuring a stable and consistent power supply. Now, let's transition to a cutting edge advance that further amplifies these benefits. Distribution automation, this technology evolves is set to revolutionize the electric utility landscape by introducing automated process into the distribution grid. Distribution automation utilizes advanced control systems, sensor, and communication technology to streamline grid operation. These distribution automation enhancing moderation and reliability are efficiency boosts by automating various tasks in the distribution systems. Distribution automation significantly reduce response time and enhance the efficiency of the grid operation. Real-time monitoring. Advanced sensor and control systems allow the real-time monitoring of the distribution grid, facilitating quicker detection and resolution of issues. Load balancing. Distribution automation optimizes load distribution, ensuring the electricity flow efficiently through the grid, minimizing distribution and improving overall reliability. Integration with smart grid distribution automation seamlessly integrate with smart grid technology, creating a comprehensive and synergistic approach to the grid management.
Distribution automation exhibits inherent imperfections characterized by intrinsic challenges that appear to examination and strategic mitigation strategies. Power grid was built decades ago and are reaching the end of their intended lifespan. This poses the reliability concerns and hampers the integration of modern technologies. It also limits the integration of renewable energy sources that can be connected to smart grids. Is the inherent nature of renewable sources like solar and wind. Efficient, efficiency energy storage solutions are crucial to store excess energy when it's abundant and release it when demand is high. Additionally, transmitting renewable energy over long distances faces technical and infrastructure limitations. Battery technologies are improving, but they still face many challenges in terms of cost, capacity, and environmental impact. Developing a low-cost, effective, and high-capacity storage system that can handle the variability of renewable generation remains a necessity. Stability and sustainability are paramount in our rapidly evolving energy landscape, and distribution automation is the key to achieving both. Embracing this innovative solution is not a step towards a more reliable grid, but we are missing economic and sustainable power to properly implement it. The high cost of distribution automation present immediate financial challenges, impacting utilities budget and potentially raising the electrical prices. Implementation complexities can disrupt operation and lead to dissatisfaction among customers. Additionally, the risk of technology obsolescence and the need for skilled more workforce contribute to the negative impact of balancing the challenges with long-term benefits and more efficient grid in essential for successful adoption. For technological advancements comes with a significant price tag. While these innovations promise a more efficient and reliable grid, their high costs present immediate financial challenges, impacting utility budgets and potentially raising electrical prices. Additionally, the risk of technology obsolescence and the need for skilled workforce contribute negative to the automation. Ethical and cultural aspects of distribution automation pose challenges that cannot be overlooked. Implementing automation in the grid raises concerns about job displacement, potentially impacting the workforce and communities that rely on traditional energy roles. Ethical considerations also come into play regarding data privacy and security, as the increased connectivity in automated systems raises the risk of cyber threats also raises. Furthermore, there is the challenge of ensuring equitable access to the benefits of distribution automation encapsulate a multi-faceted landscape. The upfront financial burden, the present immediate challenges for utilities, potentially impacting budgets and raising considerable physical prices, implementation complexities such as the risk of jet displacement and ethical considerations, the data privacy, the scoreboard societal impact. Moreover, the cultural aspect of automation make it hard for complete implementation in this current system. It also, especially, we must bring across attention to the ethical consideration and the cultural sensitive that is a must responsibility for engineers to decide upon.
Now, let's turn our attention to the modern challenges faced by the distribution automation of electric utility system. Two prominent issues demanding innovative solutions are bidirectional power flow and the imperative for flexibility to support power grid resilience. The bidirectional power flows are challenges within the increasing integration of the renewable energy sources and distribution generation. The grid experience bidirectional power flow. This means that the power can be not only consumed but also fed back into the grid. The impact that traditional grid systems were designed for unidirectional power flow, making a accommodation of bidirectional flow a significant challenge. This necessitates advanced control and monitoring mechanisms to handle the complexity associated with power flow in multiple directions. Model problem number two is the flexibility to support power grid resilience. The challenge of this is the evolving landscape of energy generation, including intermittent renewable sources demand a more flexible and resilient power grid. Factors such as climate-related events and cyber threats further emphasize the need for adaptability. The impact that this challenge is going to have for distribution automation systems must be equipped to dynamically respond to change in power generation, fluctuation in demand, and unforeseen disruptions. Achieving grid resilience requires the ability to reroute power, isolate faults, and seamlessly adapt to evolving conditions. Now, let's delve into the dynamic landscape of power grid modernization trends, where renewable energy takes center stage, necessitating a greater capacity to meet the scaling demand. This evolution prompts a closer look at the relevance and challenges associated with this transition. Number one, trend number one, that we managed to identify the renewable energy dominance. This is a trend that is a prominent trend in the power grid modernization is the increasing dominance of renewable energy sources. The transition from traditional fossil fuel-based generation to eco-friendly alternatives, such as solar wind, marks a significant shift towards sustainability. Number two is, well, this is an insight of the number one challenge is the trends is more energy needed. As we embrace renewable energy, there is a growing realization that more energy is needed to meet the escalating demand of the rapidly advanced society. The quest for cleaner and more abundant energy sources becomes paramount. Trend number two that we managed to identify the standard activity and smart grid evolution. The drive for a smarter grid is underscored by standard activities. The ENC society involvement in a smart grid initiative emphasized the need for intelligent technology-driven solutions in power grid modernization. The evolution towards a smart grid involved incorporating advanced technologies such as high voltage direct current and flexible AC transition systems. This technology enhances grid efficiency, reliability, and adaptability. The number three trend that we managed to identify is the challenges and opportunity that this brings. The power grid has evolved from central generating station to a highly interconnected system over the past century. This evolution presents both challenges and opportunities. Technological advances, including a higher voltage equipment and power electronics, contribute to a more efficient and resilient grid. Advanced monitoring and control techniques coupled with demand response and load management methods further shape the industry transformation. Now we are going to the next slide. As we navigate the landscape of distribution automation, it's imperative to explore the emerging technology and trends that are reshaping the future of electric utility systems. Let's delve into the transformative advancements that are driving innovation in distribution automation. Artificial intelligence and machine learning. Artificial intelligence is revolutionizing the grid operation by leveraging machine learning algorithms to analyze a vast dataset. This optimization enhances grid performance, detect anomalies, and predict equipment failure. Artificial intelligence plays a crucial role in predicting maintenance using historical and real-time data to foresee potential equipment failures. This proactive approach minimizes the downtime and reduces repair costs. Distribution energy resources, DER, and microgrids. The rise of microgrids, a smaller localized grid, is a notable trend. Automation ensures seamless integration into larger distribution systems, promoting resilience and optimizing the uses of renewable energy sources. DER management. Advanced automation systems are essential for effectively managing the variability and two-way power flow DERs, including solar panels, wind turbines, and energy storage. These ensure balance and stability in the grid. demand response, and smart grids. Automation enables the implementation of demand response program, encouraging customers to adjust electricity usage based on the grid condition. This aids in managing peak load, enhancing grid stability. Smart grid infrastructure. At the core of the smart grid, automation integrates advanced sensor communication network and technologies. And smart grid improve enable efficiency, load management, and foster energy efficiency. Grid edge technology. Advanced sensor. Placing sensor at the grid edge provides detailed data on grid conditions, facilitating faster fault detection and response. Decentralized control. Automation technology at the grid edge empower localized decision making, enhancing grid resilience and mitigating the impact of faults and the wider distribution network. Cyber security measurements. Security connected to systems. As automation systems become more interconnected and robust, cybersecurity measures are essential. Emerging technology focus on advanced cybersecurity measurements and intrusion detection systems to safeguard critical infrastructure. These emerging technologies collectively define the future of distribution automation, ensuring efficiency, resilience, and adaptability in the dynamic landscape of electric utility systems. Analyzing the transformative impact of distribution automation throughout the lens of the PowerNet Limited and CNC3 Saber 2 reclosure case study, we explored the challenges faced by PowerNet, including escalating operational costs and frequent outages resulting from aging hydraulic recloser, assess the role of distribution automation in addressing these challenges by adopting the 3Saber 2 recloser, known for the easy installation, low maintenance requirements, and user configurable options. Examining the tangible benefits realized during the trial phase, such as the prevention of temporary fault evolving into permanent outages, evaluate the role of distribution automation, specifically the 3Saber2 smart capabilities, including data logging and improved coordination features, in enhancing PowerNet ability to analyze events and to optimize their grid system. Interpret the broader implications for distribution automation, considering how the successful deployment of the 3Saber2 recloser has paved the way for increased grid reliability, operational efficiency, and substantial cost savings. Discussing the lesson learned from PowerNet experience and consider how this insight can guide other utilities in embracing distribution automation technology to create more resilient and efficient power distribution networks. Analyzing the profound impact of distribution automation through an in-depth examination of Puerto Rico Electric Utility Power Authority (PREPA) and their adoption of the CNC IntelliTeam's SG Automation Restoration System focus on the central role played by the IntelliRoster Pulse Closer. In the distribution automation framework, they explore how they contribute to a more responsive and resilient power distribution network. Diving into the specifics of the site automation test conducted by PREPA, emphasize, emphasizing its role in validating the capacities or capabilities of the intelligent SG system in responding to simulated events and disruptions. Evaluating the real-world benefit derived from distribution automation, including the streamlined detection of fault and rapid restoration process, leading to operational efficiency and reduced downtime. Consider the broader implication of distribution automation for utilities, highlighting how intelligent coordination and demonstrated by IntelliTeam's SG can revolutionize grid reliability. Discuss the potential for minimizing outage duration enhancing overall system responsiveness and creating a more adaptable, resilient power distribution network. Exploring the adaptability and scalability of the distribution automation solution, especially in integrating legacy systems like protection relays and recloser control, understanding how this integration contributes to the modernization of the distribution network, fostering a seamless transition toward intelligent and automation grid management. Reflect on the industry-wide significance of the lesson learned from PREPA experience, shedding light on how other utilities can leverage from the distribution automation to optimize their system. Discussing the pivotal role of smart technology in overcoming challenges faced by power authorities, ultimately paving the way for a sustainable, efficient, and responsive energy landscape.
Distribution automation offers utility companies numerous advantages, including enhanced reliability, reduced operation costs by quickly identifying and isolating faults, and it minimizes the outage durations, leading to increased customer satisfaction. It also improves the load management and reduces the energy losses, resulting in cost savings. The data collected from automation technologies can be used to predict maintenance and future planning. The problem is that the initial cost for the utility is very high and substantial. They may be resistant to making the investment. Training existing staff is also a problem, and adapting to the new technologies also poses many challenges. Moreover, automation may lead to job displacement in certain roles, raising labor-related concerns. For designers and engineers involved in power grid infrastructure, distribution automation presents opportunity for innovation and optimization. They can develop and implement advanced control systems, sensors, and communication networks to improve the efficiency and reliability of the grid. Automation also simplifies the design, responsive and adaptive grid architectures, accommodating distributed energy, resources, and electrical vehicle charging. Designers and engineers might face increased complexity in designing and maintaining distribution automation systems. There could be interoperability issues between various devices and systems from different manufacturers. Additionally, staying updated with rapidly evolving technology may require ongoing education and training. Regulators benefit from distribution automation by overseeing a more efficient, reliable, and environmentally friendly power grid. They can establish and enforce performance standards for utility companies more easily, ensuring that the grid performance meets or exceeds the expectations of the customers. Additionally, automation allows for more accurate monitoring of compliance with regulators and environmental standards. On the other hand, regulators must balance the benefits of distribution automation with the risk of utilities passing the cost of this investment to customers through their rate interest, ensuring that utilities adhere to performance standards and regulatory requirements can be challenging. Regulators also need to address the privacy data and data security concerns associated with smart meters and consumer data. Distribution automation provides customers with greater reliability and flexibility. Shorter outage durations and improved load management means fewer disruptions to their daily life. Smart meters and demand response programs can help consumers save on their energy bills by incentivizing the efficient energy usage during peak-off hours. Moreover, the integration of renewable energy sources can lead to cleaner and more sustainable electric generation. Some consumers may have concerns about privacy, data security, particularly in the widespread use of smart meters and collection of detailed energy consumption data. Additionally, there might be resistance or confusion around new rate structure or the market fund programs, which could lead to customer pushbacks. in cases where with modernization costs are passed on customers, they may have a large increase in the bills. While not a stakeholder in the traditional sense, the environment benefits from distribution automation through more efficient energy distribution and increased use of renewable energy sources. Reduced energy losses and optimized grid operation contribute to a lower greenhouse gas emissions and smaller environmental footprint. While distribution automation can contribute to a clearer and more sustainable energy grid, we may have concerns about the environmental impacts of manufacturing, maintaining, and disposing of automation equipment. To solve environmental challenges associated with production and disposal of renewable technologies, for example solar panels and turbines.
Building upon our exploration of transmission line uses in electric utility, let's delve into the pivotal role of distribution automation in enhancing key aspects of the electric grid. This technological evolution brings a myriad of benefits, each contributing to the overall efficiency, reliability, and adaptability of the grid. Number one, efficiency and precision. Automation of process. Distribution automation streamlines various operational processes, reducing manual intervention and optimizing the efficiency of the grid operation. The precision achieved through automated systems ensures the accurate and timely responses to the grid dynamics. 2. Affordability and defer capital expenses. Cost-effective solution by automating tasks such as fault identification and feeder reconfiguration. Distribution automation offers cost-effective solution. This is not only minimizing operational costs but also contributes to deferred capital expenses by extending the lifespan of grid infrastructure through proactive maintenance. Third, understanding consumption and patterns. Data-driven insight distribution automation provides valuable insight into the consumption patterns. Advanced analytical and data-driven decision-making enable utility to understand consumer behavior, facilitating better demand forecasting and resource allocation. Optimal energy generation or grid balancing through real-time monitoring and load balancing capability. Distribution automation ensures optimal energy generation. It helps match energy supply with demand, maximizing the utilization of available resources and reducing waste. Improve reliability, fault identification, and resolution. Distribution automation excels in fault identification and resolution. Automated systems quickly detect issues, allowing for swift, responsive, and minimizing downtime. This significantly enhances the overall reliability of the grid. Compatibility and regulation. Seamless integration distribution automation is designed to seamlessly integrate with existing grid infrastructure. This ensures compatibility with legacy systems, allowing for a smooth transition to automate process. And additionally, it aids in the regulatory compliance by adhering to industry standards and protocols. Enhanced distribution automation stands as a transformative force, not only optimizing operation efficiency but also elevating the grid capability to adapt to the evolving energy landscape. The integration of automation systems into the distribution network is a strategically step toward a more resilient, reliable, and responsive electric utility. In conclusion, the role of distribution automation in electric utility systems is multifaceted, encompassing crucial functions such as the management of reactive power, proactive maintenance, and the seamless integration of distribution energy resources into the grid. This transformative technology contributes to the significant advantage in the following key areas: reactive power management, optimizing power flow. Distribution automation plays a pivotal role in managing reactive power, optimizing the flow of electricity within the grid. This ensures efficient utilization of resources and enhances the overall stability of the system. Proactive maintenance. Approaches leveraging advanced analytical and real-time monitoring distributions automation facilitate a proactive maintenance. By predicting potential equipment failure, utilities can scale maintenance activity and minimizing downtime and reducing operational costs. Seamless integration of distribution energy resources. Enhanced flexibility. The seamless integration of distribution energy resources such as solar panel and wind turbine is a hallmark of distribution automation. This enhances the flexibility of the grid, allowing for efficient incorporation of renewable energy sources into the energy mix. Reduce line losses. Effective energy transfer throughout automated fault detection, load balancing, and optimizing power flow distribution automation contribute to reduce line losses. This is not only improve the overall efficiency of energy transfer but also minimize wasted within the distribution network. Improve power quality. Stabilizing grid voltage distribution automation aids in stabilizing grid voltage, leading to better power quality by regulating voltage level and addressing fluctuation promptly. The technology ensures a consistent and reliable power supply to end users. Distribution automation emerged as a catalyst for positive transformation within electric utility system, offering a comprehensive solution, enhances a grid performance, reduce operational challenges, and pave the way to a more sustainable and resilient energy future.